So these channels are mechanically gated. So what can happen is if you pull on the channel, it opens the channel. And when you relieve that tension, the channel closes. So some of these channels are open when the stereocilia are neutral. That's what's shown here. The stereocilia are straight up and down, and some of the channels are open, some of the channels are closed. So there is, even when the stereocilia are going straight up and down, there's a little bit of neurotransmitter release from the basal aspect of the hair cells, and there's a certain amount of action potential conduction or traffic in the sensory nerve fiber. So this is what, because it's neutral, we might say that's at rest. So when the stereocilia are in a neutral position. Now in the upper picture, what you see is the stereocilia are bent towards the tallest cilium. That's what's shown with this arrow here. And what that does is it increases the tension on the tip link, and that pulls more channels open. So now we have greater traffic of cations into the hair cell, and we've got greater neurotransmitter release. And when the stereocilia bend in the other direction, away from the tallest stereocilium, these tip links become kind of baggy and all the channels close. So it closes channels and the membrane potential is hyperpolarized. We've got less cation flux into the cell. So what's going to cause the hairs, the stereocilia, to bend in two directions? Well, of course, it's the sound energy. All right, so when the sound wave passes by, the hairs move with the frequency of the sound wave. So that's the case in the cochlea, sound energy. In the case of the vestibular apparatus, I'll give you a little preview, it's movement of the head through space that causes deflection of the cilia, and therefore changes the neurotransmitter release from the base of the hair cells. Any questions? Okay, so we have, here's our hairs, and it's depolarization, hyperpolarization, depolarization, hyperpolarization. Increase frequency of action potential, decrease. Increase, decrease. That's how it works. Okay. Now, there's two populations of hair cells in the spiral organ. That's in the cochlea only. So I make this point here, in the cochlea only. There's two populations of hair cells. There are inner hair cells and there are outer hair cells. So inner hair cells form a single row. Here's the inner hair cells forming a single row that spirals up and up and up the cochlea. Outer hair cells form 3 to 5 rows, depending on where you are along the length of the basilar membrane of the spiral organ. The outer hair cells form 3 to 5 rows, and they're farther from the spiral lamina. So here's the spiral lamina, here's the basilar membrane, and you can see the inner hair cells are closer to the modiolus, which would be over here, and this is the spiral lamina, and the outer hair cells are farther. Now, there's a gelatinous membrane that extends over the top of the spiral organ, and this membrane is called the tectorial membrane. I'm wondering if you remember what a tectum is. That's a word we've learned before. It means roof. So the tectorial membrane extends over the top of the spiral organ like a roof. And the tips of the stereocilia are embedded in the tectorial membrane. But that's only the outer hair cells. The inner hair cells, the tips of the stereocilia, are just extending into the fluid of the scala media. So this is a significant difference between inner and outer hair cells, must be important. Now we know that the basilar membrane will move, will flex and bend in response to pressure waves in the fluid of the inner ear. And what that's going to do as the basilar membrane moves, it's going to distort those stereocilia and alter the neurotransmitter release. The greater the deflection of the basilar membrane, the greater the movement of the hairs, the greater the neurotransmitter release. So we're going to have a stronger signal if we have greater deflection. So this next couple slides describes what the difference is in the function of the inner hair cells and outer hair cells. Now, if you look, the outer hair cells, they outnumber the inner hair cells. Remember, there's a row of 3 to every 1, so 3 to 1. So there's more outer hair cells. They must be important. However, when you look at the afferent nerves that are monitoring the bases of these hair cells, you'll find that over 95% of the spiral ganglion cells are actually listening to inner hair cells, not outer hair cells. The outer hair cells are being somewhat ignored. So most of the information going to your brain along the auditory nerve is coming from the inner hair cells. So what up with outer hair cells? Why are they there if your brain isn't paying attention to them? Well, the outer hair cells are what are called the cochlear amplifier. And what the outer hair cells do is they increase the excursions of the basilar membrane. So they make the basilar membrane, the deflection of the basilar membrane with a certain sound wave in the fluid. The deflection of the basilar membrane without the outer hair cells might be like my hands right now. But with the outer hair cells, the deflection of the basilar membrane has a greater excursion. Why? Well, they're kind of nifty cells. The outer hair cells, what they do is they make the basilar membrane move to a greater excursion because they have, in their membranes, they have motor proteins in their membranes that are driven by changes in membrane potential. So as their hairs move from side to side, and we have cations moving in to the hair cells, and so we'll have more cations and then less cations. Basically what happens is these motor proteins go from an expanded state, making this hair cell taller, to a contracted state, which makes the hair cell shorter. So they're anchored into this tectorial membrane up here. That's not going to move. What moves is it pushes down, when it gets taller, is it pushes down on the basilar membrane. So that causes the basilar membrane, the excursions of the basilar membrane to be greater. So it pushes or pulls on the basilar membrane, as it says here, increasing the amplitude of its oscillation. So this picture here shows a normal response with functioning outer hair cells, the response of the afferent nerve fibers. And without outer hair cells, they are destroyed by a drug called furosemide, so a drug that one must be careful with. They destroy selectively destroy the outer hair cells. And you can see the signal is greatly reduced. There's 100 times amplification of changes in membrane potential of the inner hair cells with a functioning cochlear amplifier. So these outer hair cells are not about detecting sound so much as amplifying the transduction, increasing the size of the transduction of the signal. So that's what the outer hair cells have been doing for you all along. So it causes a form of deafness. All good? Now, perception of pitch. So you know that sound has pitch, which has to do with the frequency of the sound waves. So in this picture, the artist has rolled out the cochlea for us, and they're showing the sound waves in blue, green, and red of sounds that have low frequency, medium frequency, and high frequency, therefore low, medium, and high pitch. And what you can see is that high frequency sounds are detected at the base of the cochlear duct, and mid-frequency sounds cause excursions in about the middle, and Low frequency sounds cause deflection and therefore are perceived at the apex of the cochlear duct. And there's a reason for this, an anatomical difference in the spiral organ from the base of the cochlear duct to its apex. So it's not uniform across its length, and in fact, it's more it's the basilar membrane itself that is modified, not the spiral organ. I misspoke. The thing about the basilar membrane is if you look at it from the base to apex, it's not shaped like that, like I just drew. I just drew a rectangle. The basilar membrane is not a rectangle. The basilar membrane is narrow, I should say, at its base, and then wide at its apex. And then, therefore, it's like a piece of fabric that's narrow at its base, wide at its apex. It's going to have different mechanical properties because of the different width. And it's like the membrane is tuned for different frequencies. So this narrow portion will vibrate in response to high frequency sounds, and as we go towards the apex, lower frequency sounds will cause vibration of the membrane. So the basilar membrane is narrow and stiff at its base and wide and floppy at its apex. The reason, and then this is counterintuitive, so this is something people get wrong if they rely on their intuition. It's counterintuitive. You expect with something that's spiraling up to an apex, you expect it to be wide at its base and narrow at its apex, and it's the opposite. So let's make sense out of it. We make sense out of it because when we look closely at the spiral lamina, remember the spiral lamina was this spike of bone that sticks out from the modiolus, and then the basilar membrane extends across from the tip of the spiral lamina to the wall of the cochlea. So the width of the basilar membrane is determined by this difference between the tip of the spiral lamina and the wall of the cochlea. So you see, if the spiral lamina recedes into the modiolus, so let's make the spiral lamina shorter. So take this off and make a shorter spiral lamina. What happens to the width of the basilar membrane? It gets wider and floppier. So you see, the length of the spiral lamina gets shorter. It recedes into the modiolus, and that means the basilar membrane gets wider. So this anatomically is why the basilar membrane is tuned for low pitches at its apex and high pitches at its base. So it's optimally displaced at a certain point upon its length by a specific frequency. It's tuned. So the spiral organ is said to be organized tonotopically, meaning that different pitches the spiral organ is going to respond to different pitches depending on where along the basilar membrane it's located. And the neurons that are monitoring that patch of the spiral organ will be having the greatest signal. So if you think for a second, here's the spiral organ, is shown by this purple thing right here along the length. And remember, the axons, sensory neurons, are monitoring the hair cells all the way along this length from base to apex. And there's the cell bodies of these bipolar neurons. And then the information flows out in the auditory nerve. Okay? Now, this deflection, this mid-frequency sound, will cause the greatest action potential traffic along the axons that are monitoring these hair cells. So it's the population of neurons firing the greatest that's going to code pitch. So that's how your brain's informed of the pitch of a sound. All good? So to summarize, you've got sound waves entering the external auditory canal. So the 1 corresponds to the 1. and the tympanic membrane vibrates. The auditory ossicles move, and the stapes moves in and out of the oval window. So pressure waves are going to begin here at number 3 and travel through the fluid of the scala vestibuli. Now, depending on the frequency of the sound, there'll be a certain point along the basilar membrane that's optimally displaced by that frequency. And the neurons that are monitoring the hair cells at that point will generate a lot of action potentials and transfer this information to the brain along the auditory nerve. The remaining pressure waves will travel down the scala tympani, and the pressure will be relieved at the round window. So that's kind of a summary of the whole inner ear. Now, how does this information, let's look at the central pathway, just an overview really. Here, you're seeing low frequency sounds at the apex, see the blue, and high frequency sounds at the base, yellow. Mid frequency again are red. Here's the cochlear nerve, carrying that information towards the brainstem. So everything from the right ear goes to the right side of the brainstem, left ear, left brainstem. And the information is delivered to the cochlear nuclei within the medulla. So everything goes to the ipsilateral cochlear nucleus. From that point onward, the pathway is bilateral, and that's important. So from the cochlear nucleus onward, information will travel through a series of brainstem nuclei and pathways through the inferior colliculus, which you recall is part of the midbrain, to the medial geniculate nucleus of the thalamus, which is the dedicated thalamic nucleus for hearing, and then to auditory cortex, which you know is on the superior bank of the superior temporal gyrus. And again, you see the color coding. So this tonotopy that takes place in the cochlea extends all the way through the pathway and to primary auditory cortex. So it's important that the auditory pathway projects bilaterally to primary auditory cortex, and I'll explain the clinical implication. If you damage, let's call this the left ear. Let's say the right ear is over here. If you put an earplug in your left ear, if you damage your middle ear, okay, so damage to the ossicles. If you damage the hairs on the hair cells in your ear, which is what happens when you are exposed to loud sounds in a loud environment for long periods of time. And if you destroy your hair cells, or if you destroy the cochlear nerve, you're going to have no information coming into this cochlear nucleus. And you will be deaf in the left ear. So damage anywhere right up to the level of the cochlear nucleus causes ipsilateral deafness. What about if you let's damage primary auditory cortex together for a minute, okay? Well, if you think about it, oops, hit the wrong one. If you think about it, the information from the left ear is going to both left and right primary auditory cortex. The information from the right ear is going to both left and right primary auditory cortex. So if I destroy primary auditory cortex on one ear, I'm still going to perceive input from the right ear, and I'm still going to perceive input from the left ear. It does not cause deafness. So a lesion in cortex, a lesion in the brainstem, other than that cochlear nucleus, does not cause deafness. It might cause difficulty in sound localization. It might have other subtle effects on your hearing, but it does not cause deafness in either ear. Now, deafness comes in two broad categories. There's what's called conduction deafness. Conduction deafness involves the external or middle ear. External ear, an example is swimmer's ear, where the ear is blocked up with fluid. Otosclerosis, which is a sort of a form of arthritis that stiffens the joints between the auditory ossicles. But the inner ear is intact and working just fine. So if you could bypass the outer or middle ear with your sound energy, you'll be able to hear or perceive sound. So in conduction deafness, hearing aids are effective because that's what hearing aids do. They bypass the outer and middle ear and send the signal directly to the inner ear, to the cochlea and the spiral organ. So that's conduction deafness. Sensory neural deafness involves the inner ear or the cochlear nerve. So you can either destroy your hair cells or you can destroy the cochlear nerve, and in that case, hearing aids are not effective. It occurs with destruction of the hair cells by exposure to loud sounds, so bring your earplugs to concerts. Ototoxic drugs that damage the outer hair cells, like furosemide was the example I gave you. Or lesion of the eighth nerve, which occurs in, say, a schwannoma, is a type of tumor that damages the eighth nerve, so damage of the eighth nerve. Those things are going to cause sensory neural deafness, and that's where people are working on cochlear implants.